And for those who have just joined us, I think we've got a bunch of people that have just logged in. Do feel free to talk about in the chat what current HVAC projects you might be planning. And we're going to get things started so that we can keep things moving on time and make sure we have lots of time for questions as well. Great, so we're here today. I'd love to welcome you all and say thank you all so much for joining us from wherever you are in Canada or in the world. I myself am Amanda. I'm joining today from the Black Forest region of Germany, and I'm one of the energy coaches with Save on Energy. And we also have today our subject matter expert, Michel Perron, joining us today. I think he's from Quebec City, he's joining us from. So we're super excited to talk to you today about estimating project savings for HVAC specific systems. So I do want to mention that Fatima is helping us produce today, and she's going to be dropping this workbook into the chat. So this workbook has so much of the information that you're going to see today on the slides. You'll have that readily available to you in this Word document. So for any of you that are interested in some of the calculations or references that we're making during the presentation, this is a really great resource for you to follow along. And Fatima, I'll just ask that you drop that in the chat for our participants. So why are we here today? What are we doing? We will be talking about using a process-driven approach to estimate savings.
I ended up on the third floor because I wasn't paying attention to the button because I thought the elevator was going down. And I didn't have.
Sorry, guys, I'm just going to ask that we make sure we mute ourselves just during the presentation, but feel free to unmute when you have questions. Okay, so we are here today to talk about using a process-driven approach to estimating savings. And this involves applying a four-step framework. Along this pathway, we will include specific and special considerations for HVAC systems and projects. So the best part of today, we have our industry specialist here. And the ultimate goal with that is that you will walk away with some expert insights to confidently address questions and be able to really refine your existing techniques for estimating savings. So there is a lot of value to applying a structured approach to estimate savings for any project. So the main benefit is that it will reduce your risk of errors that can lead to, disappointing results or even misapplied resources. So to reduce the risk of this happening, first, it's crucial to align your savings estimates with the required level of accuracy. So not all projects need the same level of detail. So tailor your analysis to match the stakes. For smaller projects, a high-level estimate might be enough, but for larger, more impactful initiatives, you really need to dive deeper into data to ensure accuracy. You should avoid over or under analyzing and really aim to strike the right balance. Secondly, try to avoid making assumptions that don't apply to your specific system. A common pitfall can be borrowing assumptions from previous projects or industry standards without really fully considering if they fit into your unique project or scenario. So every system and project is different, so take time to understand the details of your project before applying those assumptions. And lastly, make it easier to identify when saving estimates are unreasonable. So to do this, you can establish clear benchmarks and thresholds for your estimates. Also, it's really important just to trust your gut. If something feels too optimistic or too conservative, it's important to take a second look. So by following these steps, aligning accuracy levels, avoiding misleading assumptions, and then also scrutinizing unreasonable estimates, you'll really significantly reduce the risk of saving estimation errors. Let's see, okay. So this will ultimately lead you to better project outcomes. Okay, so just to give kind of a high level look at what does a structured approach look like, we've developed a basic 4-step framework that can be applied to estimate energy savings in any project. So I will let Michelle illustrate what this looks like in practice. But at a high level, the first step is to determine if your data will meet your needs by really matching it to your comfortable level of uncertainty. I'll talk a bit more about that on the next slide, but an early estimate of your data will give you more confidence in your estimated savings later on. So the second step is really to establish your baseline to understand total energy use and have a better ability to identify where errors might be occurring. And then finally, that third step is to identify and understand the various savings mechanisms of your system. It's important to think about how your system might react to changes to avoid incorrect assumptions or missed opportunities. And then finally, to estimate savings, selecting the right calculations or rules of thumb based on what you've learned in the previous steps. So to talk a bit more on the first step of assessing available data, part of that assessment might include a measure of the effort you need to put into your data versus the accuracy you require. So to know what level of accuracy you require, think about what decision you're trying to make and the risk of getting it wrong associated with that decision. So an example might be, a decision to make a big CapEx purchase. At a high level, the associated risk might be underperformance of that purchase. So this chart is really just for illustrative purposes, and the curve would be different for each unique project or situation. I think this curve can actually be even steeper for your typical project. If you make the best use of the data available to you, you can probably get greater than 60% accuracy for 20% effort. And that's really kind of what the point of today's workshop is all about. To achieve that, all you need to do is make the best use of the data that's available to you. And just on a final note here, always really stop and take stock of what information is readily available or could provide a reasonable proxy before, jumping into data collection or calculations. And we're definitely going to talk more about what that looks like. So I will briefly turn it over here to Michelle to introduce himself before we talk about kind of how this is going to work with the Q&A. So Michelle, do you want to give a little introduction to your experience and what you work on in your day-to-day?
Thank you, Amanda. Yes.
Yeah.
So good morning, everybody. My name is Michelle Parent. I'm located in Quebec City. I do work mostly in Ontario, a long story, but I do mainly energy auditing, existing building commissioning, and I do some energy modeling, either for lead building or existing building. Been doing that for about 40 years now. And like I said, it's basically what we're going to see today is a process very similar to energy auditing, and I'll get back to that. But in a nutshell, that's my background, mechanical engineer.
Wonderful, thank you. So before we turn it over for the rest of the presentation to Michelle, I just wanted to mention, this is going to be the best if you ask questions. We're really looking forward to specific questions about your HVAC systems, about your projects, in order for you to really get the most out of this. So please do use the Q&A function or feel free to use the chat. If you have something that's very specific to what we're talking about at the moment, you can use the chat and I will make sure to kind of pause and we can answer some of those questions as we go along. If you have a broader question that doesn't apply to a specific area that we're speaking about, feel free to use the Q&A button at the top. and or just put stuff in the chat if that's easier for you as well. We can definitely kind of filter through as we go along. But we would love to have participation. And also I highly suggest, if you're able to turn on your camera, unmute and ask questions directly. That's also totally fine for today. Okay, so Michelle, I will let you take over the sharing.
Okay. I'll grab the screen.
Perfect.
There we go. So as Amanda said, we're going to follow that four-step approach to try to realize as much energy savings as we can from our HVAC system. And just a side note, I said energy saving, Amanda, but very often I say people don't want to save energy. They want to save greenhouse gas and they want to save money. The energy is just the medium. It's not the end goal. So I will keep saying saving energy, but in the back of my mind, it's both money and greenhouse gas. So the steps we're going to follow, the 4 steps we're going to follow, are very similar to an energy audit. And I saw that Juan in the chat said he's doing an energy audit. So what you're going to see is very similar to what I do on a regular basis for doing energy audit. The same 4 steps that Amanda presented. And the first one, the critical one, actually they're all critical, but some are more critical than others, is really about good data. You have to know what you have to try to limit the effort you have to put in. Again, going back to the curve that Amanda showed us. So when you're talking about HVAC, either industrial or commercial, doesn't matter. HVAC is HVAC, if you ask me. You first have to wonder what is available. Do I have established equipment list? If so, it will be useful, but it's often incomplete. So you have to make sure you gather proper details about specification. A model number is often insufficient. Once you've got the equipment specification, again, for HVAC, is definitely not sufficient. You also have to gather information about how it's controlled, because very often that's the first place we're going to try to get savings is it controlled properly? So you got to gather that information during your data gathering. Try to understand the usage pattern of a given equipment. You need to talk to the people in the facility, the operators, the people, if it's an industrial facility, people that's on the production floor, to understand how the system works. And also, if there's issues, they will be very good at telling you, well, that system, it's always too cold, it's always too hot. So those are clues that you need to collect. So it's not just about nameplate, even though nameplate is really important. You have to gather more than that. You have to gather a lot of that operational information. And then you also need, while you collect that, to understand the facility's requirement. I always say, when you optimize a system, you need a target. You cannot optimize without a target. And the target is the facility requirement. Does it need to be kept at 22 degrees all year round? If it's industrial, that means the whole place would be air conditioned. So you need to establish what is the airflow requirement, the outside air requirement. All of that should also be done during this first step. It says here that you have to also identify what is metered and how it's logged. For HVAC system, it's almost never metered as like in sub-metered. It will be logged through monitoring if you've got a BAS, so you can check what's available on BAS. But like I said, very rarely do you actually get sub-metered information specifically for BS equipment, especially in the industrial sector, where you will get some metered information sometimes for larger pieces of equipment. This could apply to, like, a chiller may have its own meter. If it does, you need to identify that, know how to get it. So what do we need? Like I already mentioned, most of what you need is the specification of the equipment to start with. So for a lot of HVAC equipment, the easiest one to get is the motor size. But on its own, it's okay, but it's not sufficient depending on the level of details that you want, the level of accuracy, like Amanda mentioned, because the motor size just tells you how big the piece of equipment is. Doesn't tell you what's on what we call the brake horsepower. What is it driving? So it's really that other piece of information you need to try to estimate as good as possible. And again, it goes to what do you intend to do with that information? Do you need a lot of level of details, a lot of accuracy? then you'll need to really estimate not only the motor size, but the motor loading. And that's why it says pump flow, pump head, fan flow, and fan head. So when I talk about the head, that's the differential pressure across a pump, the differential pressure across a fan. That will actually, you can, with that information, derive what is the load on your motor. And that will add to the accuracy of your calculation done with that information. And like I said, you need to talk to the operators. So you will always start with what already exists, your equipment list. You'll still do a walkthrough because the equipment lists often are not up to date. They often do not have all the information we need for energy analysis. So we'll not have the flow, we'll not have the pressure differential. So that's the kind of information you need to complete, but you try to start from that equipment list, or sometimes previous energy audits or energy analysis that may have equipment table. Again, they need to be verified. It's like, you know, you trust, but you verify, because if it's a bit old, things change. Even the load on an equipment can change over time. So that's what you need to do, is really collect all that information, including operating conditions. Like I said, really, really important. So when you collect that HVAC data, you will obviously get the nameplate information. Like I said, very often you document that, just take a picture of it, bring it back. You know, so you have a motor efficiency, a pump has its own nameplate that you would actually collect. Like I said, how it's controlled, and you talk to the staff to know if there's issues. Good example, you collect information about an air handling unit, and you talk to the staff and they tell you, well, that system has never worked over the last 5 years. So if you were planning to upgrade that and think you're going to get energy savings compared to your current condition, that obviously would not happen. Obviously, you will get savings compared to if the system was running and you're replacing with a better system, but you need to know what are the current operating conditions, as well as any maintenance issues with a system. A little clue here: a system that has a lot of maintenance issue often hides a lot of opportunity. A pump that always has leaky seal is usually oversized and not working in its proper operating range. So that information is handy to have when you collect the information. And when we go to that third step, you'll see that knowing such things will provide you with possible savings. Nameplate information, like I said, don't just look at the motor. If there's a nameplate for the pump, there's a nameplate for the fan, you have to collect that information. Obviously, the motor itself, you want to take more than the horsepower. If there's more on it, you want to be able to collect information on the efficiency of the motor. Sometimes there's also the power factor of the motor, obviously the number of phases. All that needs to be collected. When we're talking about heating and cooling equipment, even though we will not address heating in as much depth as electrical equipment, you need still to collect the capacity of the heating equipment and the cooling equipment. And when you look at the capacity of the heating equipment, it's not, let's say you got a boiler, it's not the burner that you want. You want the boiler and the burner. And you need to know, how does it modulate? For all of the equipment that you collect, you need to know, is it possible to modulate that equipment? For a boiler, for a furnace, does it have a modulating burner? What is the turn on ratio? Same thing for any other type of equipment. You've got an air handling unit, does it have a drive? Does it have inlet guide vane? That information, again, you will judge where you need to stop based on what you want to do with the information, but those are, I'd say, the range of information you want to be able to collect. And this one is actually for HVAC quite critical, the type of system. It might seem very trivial to say, hey, we know what type of systems we have. We have a makeup air unit, and here we've got an air handling unit. But people often make critical mistakes in properly identifying their HVAC system. Just so that we're on the same page, I'm going to go through a few systems just to tell you which you need to be very careful about. It will have drastic impact on some of your energy saving measures in phase in the task step 3 and possibly step 4. So the most common type of HVAC system we see, especially in industrial facilities, but we see it quite often in commercial facility. Everybody is familiar with a makeup air unit, 100% outside air system. What actually characterize this system. And it's really important when you say, I got a makeup air unit, you have to go one step further. How is it controlled? Is it what we call a cold deck system? A cold deck system has a sensor, a temperature sensor in the ductwork. So the heating coil that you see in the little picture here, those heating coil, they are controlled not by a space temperature sensor, but by a duct sensor. And that changes quite a bit of things when you do your baselining, which we're going to see shortly, and when you do your estimate of energy savings. So always look what controls those coils. If it had a cooling coil, what controls that cooling coil? If it's a duct temperature sensor, then it's a what we call, typically there's exception, but it's a cold deck system. And you should know that in general, a makeup air unit is not a heating system. If it was, it'd be the worst possible heating system. And you can say, hey, Michelle, there's heating coil there. It's a heating system. No, it preheats the outside air to about 18 degrees, but it does not heat the space. If it does, I would advise you to find another way to heat your space than bringing 100% outside air, especially in the middle of the winter. So you also have to make sure you know if it's variable or constant speed. And last thing, when you see a makeup air unit and you do your audit, locate where the exhaust is located. Unless it's a heat recovery system that already has an exhaust basically parallel to the supply, you need to know where is the general exhaust, because one of the measures you're likely going to consider is heat recovery possible. So you need to know physically how far apart they are, and also the exhaust. Is it a clean exhaust, or is it a dirty exhaust that basically cannot be recovered, or is it a clean exhaust, a general exhaust that doesn't have any fume or any contaminant that would prevent using heat recovery? So those are the things you need to do when you identify the type of system. So it's not just saying it's a makeup air unit. There's got to be more information about what kind of makeup air unit. And like I said, if it's a standard makeup air unit, it will be what we call a cold deck system. Now, you've got this one here, very common. Again, if I go back to industrial facilities, your typical single zone rooftop unit. Unlike the makeup air unit, again, you need to understand what controls the heating and cooling coil. Usually that's a space thermostat. And that means this basically runs like a furnace. So you have to identify the system and also where it's controlled. Where is the master thermostat that controls that heating and cooling coil? And then when you do your walkthrough, you will open the outside the compartment to the damper compartment, because you want to have a look at those damper. You need to identify how much are the outside air dampers open when there's a heating or a cooling coil, which we typically call the minimum outside air. And that will give you a position of the damper, not the flow. And we'll see there's a small equation that I'm going to provide you that most people will know that will tell you the actual percentage of outside air. But have always a look at your dampers, because again, it will be useful later on when you evaluate your impact of potential measures and as well as your baseline consumption for the system. So that's a single zone system. It doesn't serve multiple zone. It has one master thermostat. And that's what we often call, by the way, a switchover system. Switchover in the sense that it will provide heating when there's a heating call and cooling when there's a cooling call, so that there's no duct temperature sensor in that system. The next one, again, very common in commercial building, not as common in industrial facilities, maybe for the office section, is the VAV system. A cousin of that VAV system would be a constant flow reheat system. Now, the one thing about that system, it is typically a cold deck system. And it's just like a makeup air unit. That means that the system right here is not designed to heat the building itself. It may have a reheat coil with fan-powered boxes at the end, but typically this heating coil and this cooling coil, they are not there. Actually, I should not say the cooling coil, but the heating coil is not there to heat the space because it's controlled by a duct temperature sensor. So when you see an air handling unit in your building, critical to identify what controls my heating and cooling coil. If it's a cold deck system, you'll see that there's a temperature sensor in the ductwork, and usually the set point will be between 13 and 18 degrees. If there's any need for heating in the space, which you typically do, you'll have either baseboard, hot water baseboard, electric baseboard, fan coils. You'll have some other piece of equipment somewhere down in the zones to provide the heating. So, and also have a look at your dampers. Always look again at the damper. What is the minimum position for those dampers? And what you'll see is a percentage opening, and again, is not equal to the percentage of outside air. So that's the three type that I wanted to present, and the influence of those configuration will be more clearly shown in the coming slides. So that's another piece of information you need to identify. I did not show you a hydronic cooling and hydronic heating system, but just, let's say, off the cuff here, you need to also obviously identify, do I have a primary, secondary cooling loop if you've got chilled water? Do you have a primary, secondary heating system, which is very common? It's a three-way valve, it's a four-way valve. And what type of boiler do I have? Do I have a condensing or non-condensing? And by the way, if you've got a condensing boiler, check the return temperature that you would typically get. And if it's above 140 degrees Fahrenheit, your condensing boiler is not condensing. It just has condensing in the name. It doesn't have condensing in practice. So always keep track of that information. And again, it depends on the level of evaluation you want to go to. If you want to be very precise, you need to collect that type of information. So that's about what you have to document when you walk through the building for your systems. And I told you there was a short equation that was going to give you, when you look at your damper and you see that it seems to be open about 10 to 15%, but you want to know what is the actual percentage of outside air. You can use this equation, let's say when it's fairly cold, about 0 degrees or below, you measure the return temperature. If you don't have a measure, it's about 23 degrees. It's a very common return temperature. And then you will measure the mixed air temperature. If I go back to that slide here, the mixed air temperature is located right here where the returned air and the outside air mixes together. You'll measure that temperature. Sometimes you have to take an average because there could be stratification in your system. And then you'll divide that by the return temperature minus the outside temperature. This will give you a good estimate of your percentage of outside air. And because dampers are not linear, it is often more than the damper opening. You may see 10% damper opening, and you could have 20% outside air. So that's why, again, depending on the level of accuracy you want, this one is quite important to do if you want to be more accurate. If you've got measures that will impact heating of outside air, cooling of outside air, you should definitely try to apply this. If you want to go a step further, you'd have to get it measured. Very often from a balancing company would come in and measure that unless you've got your own equipment. But you can do it with the temperature, and it's typically pretty good if you do it when it's cold enough. Last item about collecting information. When you collect information, I've talked about HVAC systems, but the building envelope does impact your HVAC system, does impact how much heating and cooling is required, as well as it will impact, for example, your condensing boiler. If you've got a condensing boiler, what temperature you can return to, what temperature you can supply. So the quality of the building envelope. So you may need to collect information. I usually would not do that unless you plan to do something with your building envelope, or you want to have a whole energy model, let's say using red screen of your building. So you'll have to collect wall area, roof area, very importantly, overhead doors if you're industrial, and get some estimated value for the R value of those components. If you don't have any idea, you look at the type of construction or you look at the age, and it will give you kind of good estimated values. You know, there's some buildings that are pre-1970, and you know the walls have not been insulated. You're probably safe at using something between R5 and R10 at most. And then, you know, between 1980 to 1990, R12 or around there, a little R10 to R15. And then more recent, you should know when it's more recent. Now, you might think those are really low values. I know I've got more insulation, but those values include all the thermal bridging. For anybody that has done energy modeling and have to use the thermal bridging models, you'll know that a wall may have R20 insulation, but its actual R value may be as low as R10 because of all the thermal bridging, depending if you've got metal beams or wooden structure, it can really drop. Well, the roof, you usually know because roofs are redone and usually you know about how thick insulation is on your roof. So it's a little more available for the roof. But again, you would collect that information only if you know you're going to be needing it in doing your evaluation for your measures. Or if you want to do, like I said, a full-fledged energy model of your building using a tool such as Red Screen, which I will show you very quickly in the coming slide. So Amanda, I was going to ask people, what do you guys typically have in terms of information for your HVAC system?
Yeah, I'm super curious as well. So feel free to unmute yourselves or go ahead and throw it in the chat. What data are you already working with? Or maybe what data do you think you have that you haven't quite looked at yet that's available for your HVAC systems? Anyone want to share?
And I'll say most people probably have a list of motors. The list of motors is one of the more common one that's available, but usually it stops there. They don't have airflows and they don't have pressure differential and stuff like that.
We did have one question, Michelle, during your presentation that was related to data gathering. And the question was around a retrofit project for a hotel. So the hotel has rooms and there's 300 units of individual HVAC systems that have to be replaced. So they were curious about incentives, which I provided some information in the chat about different incentive programs that they might want to look into. But also, what would you suggest, what kind of information to be collected for that particular project would be good? Maybe pointing them to some of what you already said, but also if there's anything else that you think would be relevant.
So typically, like in hotels, they'll have what we call sometimes PTAC unit, package terminal air conditioner. Depending on what they want to install, they would need to know what is the capacity. It's usually very easy because it's very repetitive. You may have slightly different size rooms and corner rooms that have larger units. So usually you can go and take a typical, let's say, middle unit, and that can apply to all of those units, and it will give you the size that was there. And it will give you an indication of what should be going there. Unless you take any other measures, you could decide to redo a whole building load assessment, or you could say, hey, I had a 1.5 ton unit. I'm going to put back a more efficient 1.5 ton unit. So by knowing what's there, it will give you guidelines on what you could be replacing it with. Without having to, unless you do other measures, like I said, you change windows, you insulate wall, then your whole load calculation will change and you'll have to start from scratch, basically.
Great. Thank you for sharing that. And then I think we did get some responses to that question in the chat. So Ashish was saying they have BAS data, which is great. And also Greg mentioned BAS data is available, or when BAS data is available, you typically have scheduling, sequences of operation, and trend logs of temperatures, damper positions, etc. And then Juan was saying they have data plates and then also use estimations. So those are some things. Cameron also has the Limaquid data, they mostly use thermal efficiency of AHU and building envelope characteristics. And those values get inputted into Red Screen to determine estimated energy consumptions of that AHU unit.
And I'll talk about that in a minute. A couple of things here that you have to be very careful about. BAS data is great because it tells you damper opening. It's damper opening. I like the fact that we say damper opening. When you see BAS and you ask the operator, what's your percentage of outside air? They're going to say 10%. And that's wrong. It's 10% damper opening. It is not 10% outside air. So always be careful when you look at your BAS data. If you do have the mixed air temperature and you've got the return and outside air, you will be able to correlate that percentage of opening of your dampers to the actual outside air. Like I said, it has to be cold enough to use that equation. It's easy to put in Excel, and then you get your monitoring data. So just be careful about that. And the thermal efficiency in red screen. But you have to be very careful. When we get nameplate information, it's nominal. It's going to say 80%. Don't ever enter 80% in red screen. Red screen uses that as its annual efficiency. There's no equipment that I know that has an annual efficiency equal to the thermal efficiency. It's always 5 to 10% lower, depending on the quality of your equipment. So never carry over the nominal efficiency directly to red screen without doing a correction downward to account for, the purge cycle, any kind of short cycling that would basically really reduce your annual efficiency. Everything in red screen is always based on annual efficiency. So thank you, Amanda. That was great.
Yeah, no, those are such good tips, and I think they actually fit really well into this next slide in being able to common errors and
yeah, exactly. So
yeah.
The common errors, obviously, if you don't gather operational data, you'll have to go back because you will need the operational data. Don't assume operational data. It's probably one of the key variable. Even when you do like that 20-80 rule, you just try to spend 20 of the effort to get 80% of the quality information. Operational data is really important. If you misidentify your HVAC system, I insisted quite a bit on that. If you have a really poor estimation of the amount of outside air or air, actually, because one impacts the other, that can lead to really big mistakes. If you say, I'm going to put heat recovery on this unit, and you forget that there's 5,000 CFM of exhaust air, and your unit is bringing 5,000, and that exhaust air you think is not impacting your air handling unit. It does. It's stealing the outside air from the unit, so the unit is not returning it to itself. It's actually being exhausted elsewhere. So your heat recovery would give you nothing. So you got to be very careful about how that air balance is in your building. And obviously the O&M issues, like I mentioned before, very important. You need to know if the system's working properly. Is it short cycling? Because if it's short cycling, such as a boiler, your efficiency will drop not by 5%, but by 15%. So try to get a good estimate of that. So obviously, the outcome of this step is to get a reliable set of information, and you will have gaps. At least you'll be able to document. And if you need to dig deeper, it will allow you to know where to dig, because that will allow you to identify where you're lacking information. Once you have all of that, it's actually quite a bit of work to gather all that information. You should establish, as a step 2, the energy baseline. And the good news about the energy baseline is that whatever method you use to establish that energy baseline, you're going to probably use to evaluate the energy savings from the measures you're going to propose. It's very often the same. There are times where it's not the same, I'd say, method or tools, but it's very common to have the same. So it's kind of, 2 birds, 1 stone when you establish the baseline. So, and the baseline will allow you to know how much energy goes to a given piece of equipment. So your savings estimate can never be higher than that. I've seen many times where vendors come in and will promise you the moon. You do your baseline and like, I'm not even using that much here. So they're promising me more than I'm using. So you need to be able to establish that baseline. And obviously that baseline is typically, unless you do an energy model, like I said, full-fledged energy model, we talked about red screen, and I will have about a few warning about HVAC in red screen. You got to be very careful, but you will build that load inventory based on what you did. You probably have all that collected in Excel. So very often what we'll do is do a thermal balance and an electrical balance. You could do also a cooling balance where you have, let's say, 3 tab in Excel when you do an audit without an energy model to get that baseline information. And very often what it looks like, and that's taken from a Natural Resources Canada document. Basically, you have different methods. when you have some simple equipment, such as lights, computers, stuff like that, you can have that one sheet. We call that the simple load method, where you will define either the description of the load. In this case, they use the description of the space, and it's lighting, and they say, I've got 50 lights of 47 watts. So obviously, the kilowatt total installed is 2.35. It's A times B. Now, if you do that for lighting, and it's the old-fashioned fluorescent light, got to be careful about your wattage. The errors can creep in everywhere, so you got to be careful how many lights are actually being used and are not burnt out permanently because they're never changed. And then if you've got, let's say, two T8 or 32 watts T8, that's old-fashioned fluorescent. Don't enter 64 watts here because your lamp is not drawing 64 watts. That's the nominal wattage of a fluorescent, but it has a ballast, which has a ballast factor. So what you will enter here is the actual drawn wattage by the equipment. Once you've got that, then you will define the operating period. And for lighting, it's just straight hours. That's pretty simple, but sometimes it is where we make the biggest mistake. The wattage, once you've got, you take care about the load and about, is there a ballast? Is there anything else that can modify that wattage? Where your biggest error will be is on the hours. And sometimes it's difficult to assess the hours. So you've got to spend some time trying to assess, do the best assessment possible of those hours. That's why I said talk to people when you do your information gathering. And then once you've got that, obviously you get your kilowatt hour. So it's like the most simple equation. If you want to go one step further and say, how much does it contribute to my peak demand? Then you can say, yeah, I'm going to say this load will be present during my peak period, midday, the lighting is on. And then you can say, what's the diversity factor? The diversity factor is a bit like the hours for the kilowatt hour. It tells you, if I've got lights, are they all on at the same time, or there's 50% that will be off? So it's not 100% of the kilowatt that happens on peak, it's only 50%. So there's a large uncertainty on the diversity factor. There are resources you can try to find about diversity factor, but honestly, it's usually based on your walkthrough. You observe, you talk to people, and then you can get a diversity factor, and then it will tell you what is the contribution of that load to your peak demand. And obviously, if you do that for all of the equipment that draw electricity for your building, you should be able to calibrate that to the monthly bills. And if you do this inventory for everything, including any process load, then you should match. And if you don't match, then the most likely place you're going to have made an error will be on the hours for the energy and on the diversity factor for the demand. So that's the simple method for establishing your baseline. And you're going to use that same spreadsheet for your measures. Say, I'm going to change my lights. Well, you're going to copy that table and you're going to change the kilowatt to a new kilowatt and or wattage to a new wattage. And boom, you're going to have your savings right away. So this table can be used to get your energy savings for anything that will change either the load in watts or the operating periods in hours. But like I said, it's easy, doesn't mean that it's accurate because it is dependent on your estimate for the hours. And by the way, the hours, I call them equivalent full load hours. So let's say, and we'll see that on the next one. Actually, I'm going to go to the next one. So there's the just the identification of the columns. The next one will give me a chance to tell you about the hours here. In the previous slide, you saw that I wrote at the bottom of the slide that there are equivalent full load hours. If you've got something that is plugged in, but cycles on and off, let's say I had a refrigerator in here. It's plugged in all the time. It may have a 300-watt compressor, but that compressor is not on all the time. So you don't enter 8,760 hours. You will have to enter what is your estimate of the cycling of that load. So, and that is actually translated into equivalent full load hours. Same thing if you've got something that modulates. For some reason, you've got a load that modulates between 0 and 100%, you will have to enter basically the percentage of that load times 8,760 hours to get the equivalent full load hours. And that's what you will do on this sheet, if you've got another sheet that's for motor load, dedicated just to motor load, you will enter the number of motors you have, the horsepower, and if you were able to measure, let's say, the flow and the delta P for a fan or a pump, you can actually get your load factor. I'm not going to go into details. If you have no idea, enter 75 or 80%. Motors do not run fully loaded. It's very rare. I'm not saying it's impossible. They usually run at 75 to 80% load. So if you don't know any better, enter 75%. Let's be conservative. Then you will enter the motor efficiency. It's usually quite high. 78% in this example is quite low. And if you multiply all that together times 0.746, as you see at the bottom, because we want to go from horsepower to kilowatt, that will give you the total kilowatt drawn by this motor. And now you will have to enter an equivalent full load hour. Now, if you do the table for a month, obviously, that will be equivalent full load hours for the month. You can enter it for the year, then it becomes equivalent full load hours for the year. This is an air compressor. That motor, that compressor is not going to be running all the time. So your equivalent full load hours have to account for the fact that it will cycle on and off. Depending on the type of compressor, it may actually draw 60 to 70% of its power, even when idling. So that will impact your equivalent full load hours. And I know that makes it much more difficult, but that's the challenge of doing those inventory. You do have to get a good estimate of those full load hours. Now, if you've got a BAS and you're trending that equipment, then you can get sometimes the equivalent full load hours, depending on the quality of your BAS, the type of information that it's trending. So that's for motor load. Now, if you also measure current and voltage, you can do the same table. And in this case, the difference is obviously that you will have to apply the formula at the bottom. And depending on the number of phase, if it's one phase, you multiply by 1. If it's 3 phase, you multiply by 173. And basically, the rest is identical. You get your kilowatt based on your amps, your volts, and the equivalent full load hours. If you've got a VFD, I would probably not, I could use that. But the load factor or your equivalent full load hours would have to be corrected very significantly by what we call the affinity laws, which I have in the next slide, because the power to a motor varies to the cube of the speed. It's not linear. So you don't just say my motor's at 50%, I'm going to reduce my equivalent full load hours by 50%. That would not work. You have to correct by the affinity law, which says that the power will be reduced to the cube of the speed reduction. So that's the third method, where you will have now your inventory of all your electrical equipment. Now, for the thermal equipment, you would have to do something similar, but usually I don't use the boiler size times the number of hours. If you do a very, very rough estimate, you could always do that, but it's usually quite inaccurate to do that. You're better to look at your load. So let's talk about the ventilation load. When you have a ventilation system, the easiest one would be a makeup air unit. You will use the following formula, and sorry about formulas, but when you do an inventory, you do have to use them. So it's the amount of outdoor air times a, I call it conversion factor. It's the density times the specific heat, 1.08, times the heating degree days. The heating degree days are for the period for which this system is operating, and it's also based on the temperature at which it's supplying. So a makeup air unit supplying at 18 all winter long, Monday to Friday, you would get the heating degree days for 18 degrees. And I have a website that I'm going to show you before in the next slide, where you can get that information. Then you multiply that by 24 divided by the efficiency of the heating system. So if it's gas-fired makeup air unit, you divide by, let's say, 0.75. If it's electric, obviously by 1. If it was a heat pump, you divide by the average annual efficiency, let's say 2.5. So that's how you would get, and you would do that for every single air handling unit. That's for a makeup air unit. Now, if you've got a VAV system, anything that is multi-zone cold deck, so a reheat system, a VAV system, you can use the same formula with a very important distinction. Your temperature where you're going to calculate your heating degree days has to be calculated based on this equation. And again, apology for the math here, because what happens with a cold deck system that has mixed air is that your supply temperature will be your limiting factor in determining how much you need to heat that outside air. Because when you mix 90% return air with 10% outside air, you're basically heating your outside air. So your return is your main heating source. You will only start heating the supply air when it gets really cold outside and your return air is unable to preheat your outside air, let's say, to 18 degrees. So the quick formula here is you take the supply temperature -1 minus the return temperature times the return flow divided by the percentage of outside air. So that was return flow in percentage. And that will give you your balance temperature at which you will evaluate your heating degree days. And you will see that for most VAV systems that run at 10% outside air, that balance temperature will be in the area of about -15. That means you have no heating in those VAV systems until you get to -15. So you will get to evaluate the heating degree days for that equation for a VAV system. Same equation as a makeup air unit, but a makeup air unit, the HDD would be evaluated at 18 degrees. And for a multi-zone system, such as a VAV, a cold deck multi-zone system, at -15. Now, where are you going to get those heating degree days? There are some really easy resources. You can go and you can use Red Screen. It will provide you heating degree days at different balance point temperature. And there's a website called degreedays.net where you can enter the schedule that you want to have the heating degree days and your balance point and the location anywhere in the world, and it will give you those heating degree days. So it's, even though there's some pretty easy math involved, you can get the estimate for heating for your cold deck mixed air system. And by the way, this equation also applies for single zone. The only difference is that the outdoor airflow is obviously your supply flow times the percentage of outside air that you would have for that system. So if you don't use this equation for cold deck system, you will end up calculating a high heating load for that VAV system. And it will be completely wrong, and you will draw the wrong conclusion with regard to your efficiency measure. And when I say wrong, it's not just like 5% wrong. It's going to be wrong like 95% wrong. It's going to be very bad. So make sure you use that. Unfortunately, Red Screen does not do that calculation. So if you've got a cold deck system in Red Screen, a VAV system in Red Screen, never, ever use it to evaluate the heating load on that system. I would disable heating for those systems in Red Screen. There are workarounds. I don't have time to present a workaround, but just be very careful. Cold deck systems are not modeled properly in Red Screen. They're not modeled at all, even though there is a workaround. And if you use it, you will get the improper answer. So basically, that's how you would get your heating and cooling load. For cooling, you can use the same if you want. That will give you the sensible heat. If you want to have more, you'll have to use the enthalpy, and that means that's a manual calculation. Or you can use the same equation as before, and as a very rough estimate, replace the 1.08 by 1.5 to account for the latent load, so the humidity that will be taken out by your cooling coil. But that's a very rough approximation, obviously. That can vary, but that's how you could do it. And finally, we're going to get to step 3 now. After this, if you do have to deal with the building envelope and say, I want to know, what's going to be the impact of building envelope measure on an HVAC system, it's very, very difficult to do that properly in a manual manner. So I usually would go with Red Screen, where you can easily define a building envelope where you'll enter the area, the R values, and you will define a temperature schedule that will say, hey, I'm keeping that space at 22. That's by far the easiest way of doing building envelope at a high level. There's other tools. I don't know, I'm not here to promote Red Screen, but it is an easy one to build that. So then you will, if you have a full model, analytical model, you can reconcile to your bills, like I said before. Now, the big errors, like I said, is not considering that balance temperature for VAV system would be a big mistake. not having a proper load factor or equivalent full load hours, that can result in really poor estimate of your energy use because you're overestimating. Usually it's overestimating the number of operating hours. And if you're looking at demand, like I said, it's the diversity factor to say how much of that demand is on my peak. That's where you'll make the biggest possible error. So I'm a little short on time. I'm just going to say, if you do have approach that you're using for estimating your HVAC energy consumption, or if you have any questions, I invite you to put in the chat and we'll get back to it after I'm done with step 3.
Yeah, we have a couple questions, one in the Q&A and one in the chat, but we can come back to it.
No, you can go for that. A couple of questions.
Yeah, I think the one by Greg is specific to the equation being imperial, and so the 1.08 CFM delta T is an imperial equation that uses temperatures in Fahrenheit. So should this equation therefore use, I think it's heating degree day based on Fahrenheit temperatures?
Yeah, it would be all Fahrenheit. Even though I did say 18 degrees C, it's all, you're right, Greg, it's all in imperial. If you want to use the same equation in SI unit, you replace the 1.08 by 1.2 and the CFM by liter per second and everything else in Celsius. But you're right, the heating degree days would be in degrees Fahrenheit. And degreedays.net, the website you saw there, will give them to you both Celsius or Fahrenheit, and I usually would go Fahrenheit. So because I'm old. When you're older, you use Fahrenheit. So now we're on the step 3, which I often find a challenging step. So you did your collection, you did your energy balance, even if it may not be for the whole building, but you got a baseline. Now you need to understand, how am I going to save? Sometimes it's easy, sometimes it's not that easy. If you've got a really efficient building, you try to figure out, how do I save? And that's what we call here the saving mechanism. And usually for HVAC, unlike some other, let's say, industrial system, most people have a good feeling of the saving mechanism that are usually in play, which means usually it's reducing the amount of time something runs, reducing the load that something has to answer to, and improving the efficiencies. There's probably another one by going also, and I did not put that in there, but going with renewable sources would be another one at the very end of it. It's usually not the first one we tackle, but that's what you have to look at. Can I use less? Can I reduce the load on it? And can I improve the efficiencies? And by improving the efficiencies, that doesn't mean changing the equipment. Very often the equipment that we have are not running at peak efficiencies for various reasons. Can be maintenance, can be controls. So really you will have to look at that. And most of the time, a given measure will impact more than one of those 3 items. It will often be 1 and 2 or 2 and 3 and stuff like that. So the first thing you have to look at, and when we do a recommissioning, first thing we always find is reducing waste. It's amazing how many systems, even though they're ran on schedule, are not running on optimal schedule. Some people will start their makeup air unit 3 hours before occupancy, and I always ask why. They say, well, it's cold outside. I've got to start the system early. Well, you're just shooting yourself in the foot, because a makeup air unit is not a heating system. It's purely ventilation. Start that system half hour or 15 minutes before actual occupancy. So look at all your system and ask yourself, is it running to meet the requirement? That means, do I understand what my HVAC system is supposed to do, what it's supposed to provide in terms of services? If it's only a ventilation system, such as a makeup air unit, I don't need to start it early. VAV system, I mentioned, it's a cold deck system. It's not a heating system. You don't typically need to start it early in the winter. So scheduling optimal start is one of those opportunities that will impact both your load and your equipment runtime. So you will hit, like I said, 2 of those saving mechanisms. When you look at your HVAC, proper operation of dampers, are you do you provide enough outside air? Are your dampers controlling properly? Sometimes you don't provide enough outside air, oddly enough. And even though it may not bring immediate savings, it may put you on the path to identify savings. If your outside air is driven by exhaust, and you're throttling down your dampers to 5%, I'm sorry, but you're not saving because your exhaust is driving the outside air. And that means now the outside air is coming from the door, from the cracks. You're depressurizing your building. You are better off bringing that air through your air handling unit. It will be filtered, it will be conditioned. And maybe then, like I said, you can say, hey, do I need all that exhaust? So always keep in mind proper operation of dampers. And are they, airtight? When I ask 10%, do I get 10% outside air, which is unlikely. So you can actually get savings out of that. Unoccupied mode shutdown and restart mode. When you've got single zone unit and they provide the heating for the space, you got to find a way to not get that system to run 24/7 like if it was an occupied building. Try to have a night mode. Maybe that means a VFD on the motor. So you reduce your load and you reduce the equivalent full load hours. So again, you hit more than one of those saving mechanisms. And heat recovery, too many times I've seen heat recovery device installed, but not running properly. No diagnostic done on their heat recovery. So you want to reduce the load, another saving mechanism, by using properly your heat recovery. It's easy to diagnose a heat recovery device. You look at the delta T on one side, look at the delta T on the other side of your heat recovery device. That delta T on a balanced flow should be about the same. If it's not, and you got a really high delta T on one side, a very low delta T on the other side, the high delta T side has not enough air. So maybe it's because you're exhausting somewhere else and there's very little return. So you're not recovering. Again, that will be the equivalent of waste. So reducing waste in recommissioning, we get 50% of our savings from optimal scheduling. And that doesn't mean just optimal start. It's just by knowing the system and reducing it, doing setback. Some people think setback don't save. It doesn't save because in the morning, the system has to catch up. Well, that's a misconception. Setbacks reduces your load, will always save. You have to be careful to do it properly so you don't create comfort issues. But if somebody tells you setback doesn't save, that's wrong. And then, like I said, you have to achieve the best performance of your existing system. That will hit also multiple of those saving mechanisms. Very often we have systems that are efficient, but are not used efficiently. You've got pumps with VFDs on the pumps, and very often pumps are duty and backup. But I've seen too many times pumps with VFDs that are supposed to be duty and backup running in parallel. That is not efficient in most cases. If you want to go with the default safety efficient mode of operation, you should lead lag pumps that are in parallel, even if they have VFDs, not run them in parallel. You've got high efficiency chillers. They should be run in parallel as much as the load will allow because they're typically more efficient in parallel. Again, you got to be careful about, do you have to bring on a new cooling tower? Do I have to bring on more chilled water pumps? That may actually impact when you're going to go to parallel, but it is, again, using your equipment to the best efficiency possible. Condensing boilers, too many times I see condensing boilers being run lead lag. That is not the way to run efficiently your condensing boilers. You should run them in parallel as much as the load and the turn down ratio of boiler will allow. The turn down ratio that you documented when you did your walkthrough becomes really important at this stage. So when can I start running my systems in parallel? So there's a more example here. And like I said, a lot of those will hit more than one of the saving mechanism because it will reduce the runtime and very often will reduce the load on your system and improve the efficiency, which was our third saving mechanism. And obviously, you can also optimize your supply by now installing more capital intensive measure. And that's very often will be either reducing load or improving efficiency, installing heat recovery. It's not there. So it's not like the one before where I said you have to make it as efficient as possible. You're really improving the process by reducing the load. Same thing with destratification fan. It's basically reducing the load. And you can then go with high efficiency chillers and boilers. So those are all about improving efficiency and reducing load. They're typically not our first measures to implement. You don't want to invest heavily in equipment that may end up being oversized because your other measures from reduce the load. So that would actually allow you to select a smaller equipment. So you should always go with the first two steps that I showed you here and use this last one for, I'd say, achieving really much higher savings than the operational measures that we saw before. Now, when you need to evaluate those measures, you will typically use, like I said, the same baselining equations that I showed you before. The assumptions that you can make, the common errors would be, for example, to not use the affinity law for VFDs, where you reduce motor speed by 10%, you will save 25% of the electricity, not 10%. So you got to be very careful about your savings calculation so you don't make those mistakes. And obviously, if you follow the same baseline equations that you saw before, you should be good. You should have already used the proper equation to establish your baseline. So once you finish step 3, you identified your measures. You know how they're going to save. You basically already know how you're going to do step 4, which is your savings calculation, because you're likely going to adapt what you did for your baselining. And so here we ask you, when you're looking at your energy audit, what are the saving mechanism that you try to take advantage of through your measures? And Amanda, I'm going to say people will probably do one, and the first two mechanisms I talked about are almost always there. The last one, depending on your budget, you may or may not consider it because it's usually a capital intensive type of measure.
Yeah, and I think we can ask people to put the answer to this question in the chat, and we can keep things moving. But I did, Cameron had a question regarding what you were speaking about specifically. So maybe we could do the quick answer to that now.
Yep, go ahead.
The question is, are unoccupied shutdown modes only possible when VFD are present, or can BAS systems stand in on its own to conduct this feature? So the role of BAS systems in managing that.
So the unoccupied mode shutdown, typically, if you've got zone level heating, you don't even have to worry. Your BAS will just shut it down, obviously. The only time you have to have let's say you have to be careful about unoccupied mode shutdown is if your system that you're shutting down is actually providing heating to the building. Usually cooling is not an issue. People will stop it and the building will warm up and you just early start the next morning. So if your system provides the main heating source for the building, then your BAS could take over without a VFD, but it would lead to restart. So you would have more stop and go for your system. You would usually have a minimum runtime, let's say 45 minutes or an hour, so you don't short cycle your motor. But you can do it with a BAS without having a VFD. If you have a VFD, it makes it easier. It's not as hard on the contactors because you don't start and stop, but you got to be careful. If you stop, make sure you got a good dead band so you don't short cycle and you have a minimum runtime for your equipment. Then the BAS can do it without investing in a VFD. So now we're getting to that last step, the very critical step, which is the savings calculation. You can include, the way you can proceed is using rules of thumb. I try to stay away as much as possible from rules of thumb because you never know if they were developed for your specific application. Engineering calculations is what we typically would do in most audit. Complex modeling, it's really for, high stake project, that's capital investment, and complex modeling is not red screen. Red screen is engineering calculations. It's just a different way of doing engineering calculation. It is not modeling. So be very clear about that. If somebody tells you I'm doing an energy model using red screen, it's an energy accounting software. It will account where the energy goes. It doesn't really do what we would typically call energy modeling. So those are your options. And like I said, you're probably going to retain what you used for your baselining unless the measure that you have is completely outside the scope, such as putting PV panel. Then you would go to red screen, for example, or other software. Any renewable energy, you could use red screen. Obviously, your baseline equation will not be able to give you that. I told you for the any place you're going to install a VFD, the flow will be modulated proportionally to the VFD speed. So your savings calculation can be based on a and I'm going to zoom on this here, that's the kind of scary affinity laws. I say scary, I should not say that. It's so your flow will vary to the same proportion as the speed. Forget the head here, we don't care about that one. But your power will vary to the cube of your speed change. So those are the equation you need to apply when you go to a VFD. So it may or may not be in your baseline equation, depending if you do have VFDs or not. If you don't and you have a measure, do not use proportional savings for motors. I know I'm repeating myself, but it's quite important. So you're going to use your baselining equation. You're going to say, how much do I reduce? And you have to be very careful again. When you put a VFD and you say, hey, it's going to reduce the speed by 50%, you have to be very careful about your reduction in speed, because often people will overestimate the reduction. Very often you go on site and you see VFDs and they're running 80%, 85%. So you've got to be very certain of your reduction in speed that you think you're going to achieve, because that is then exponent to the third, or 2.7 if you want to be more conservative. So it's really going to blow up your estimate to a very large saving. So be very careful. For building envelope, just go back to red screen. It will allow you to change the R value for what we call the proposed case. If you want to know if I do a setback in that space, what will be the impact, you can actually go in red screen for the same model that you use for your building envelope and just change the temperature at night in red screen. So that's pretty straightforward. Again, don't use red screen for the cold deck system. You are way better off using the equation that we saw in the baselining section here. If you got destratification fan, you can use red screen where you will model the roof separately, because a destrat fan, what it does, it reduces the temperature at the roof level, so reduces your roof heat losses, and may also reduce some of your exfiltration losses. It won't reduce the losses per se, but it will reduce the temperature at which that air is being exhausted through exfiltration. And again, you can use red screen by defining a specific component that would be a building envelope that only has a roof and only has exfiltration, and then you change the set point for that roof and for that zone. Just it won't impact the wall, will just impact the roof, and it will give you the impact of a destratification fan. So it's short workaround to do destrat fan in red screen. And obviously, for equipment sequencing and ventilation unit, you will use the same baselining equation. Where you have to be, again, very careful. If you change your heating system, you say, I'm going from regular boilers to condensing boilers. Ask yourself the question, how long during the year will my condensing boilers be condensing? Stay away from automatically using 90% or 93% efficiency for your condensing boiler. Very often they will run around 85 to 88% because they will not be in condensing mode. So same baselining equation, you do have to have a judgment call on what efficiency you're going to be using. For exhaust air heat recovery, use the same equation that we saw for heating, that one with the CV1 and 1.08. You just multiply by 1 minus the average yearly effectiveness. And again, it's a judgment call. If you are installing a glycol runaround loop, you'd probably enter 50% effectiveness or 0.5. So you would basically reduce the load calculated for that system by 50%. So that's how you would use your baselining equation, transport them here, and get your savings. And that would give you, pretty high level, but that's in an acceptable range for getting I'd say, do I need to dig more if I need to invest? So I'm putting heat recovery on that system. I did the calculation. The payback is 20 years. You can dig as much as you want. You're not going to take it down to 5 years. So if you're at 7 years and say, hey, maybe I need to measure the flow, maybe I can make sure I've got the proper effectiveness, and then you can get to more accurate results. So that is the 4-step approach. Get the data from your building, from your system, establish a baseline, document it properly, look at all the systems and understand your saving mechanism, and say, what measure can I implement that will take advantage of those saving mechanism, and then do your savings calculation. You will end up with something that should look like. I'm going to show you a very quick example, an audit that I did in a food packaging plant at 30 air handling unit. By the way, AHUs, air handling units, RTUs, rooftop units, they're basically the same. One is outside usually and one is inside. That's kind of the convention. So you would do, so let's say you're going to do that. You would do an inventory of the system. So you would go identify, and actually this table I had to cut off because it's too big. You have the tag. Always make sure you have the proper tag. You'll find sometimes that there's like 5 RTU1 in some buildings. So try to clean that up at the same time. The model number for rooftop units, very often you won't get all the information, such as the motor power, unless you open the motor compartment. So the model number will allow you to go on internet and get the actual horsepower for the fan. You get the flow, cooling capacity, heating capacity. Now, if I had more place, I would have equivalent full load hours. So what we discussed before to do the full calculation. So once you've got that table, and say, I'm going to do now my inventory of my baseline. So that's the first step, inventory. Second step is apply the equation. So the motor energy, I've got a 40 horsepower fan, 0.746, 0.75, and actually I forgot to multiply by 1.73. No, that one's it's correct. Sorry, it's correct. It's not amps and voltage, it's horsepower. So that would be the equation that we saw before. Most of you would be very familiar with that. You do it for all the lines. That's okay for constant flow system. If that system had a VFD, I would have to put another parameter in there, which would be the speed exponent to the cube. And actually, I don't use cube. I use 2.7 and would be the same equation, but would take into account the VFDs, and obviously would drop that 196 quite significantly. But in this case, for the sake of the example, I don't have a VFD, and I could decide to propose a VFD, and obviously then I would just multiply by the speed to the cube, subtract the two results, and get my savings. So baselining would work like that. You do that for every single one of them. You get your electricity table. You can sum all of that. That will be your total ventilation. If you did that for all of your equipment, you could balance to your monthly energy bill. That's preferable to have that, but if you just do a partial audit, if I can say, you will not have that. So use the same baselining for all of that. And obviously, we would do the same baselining for thermal energy and cooling energy, line by line, using the equation that CV1 times the heating degree days and all that. So you would, and again, once it's in Excel, it goes pretty fast. It's not too difficult to implement in Excel. And you get to step 3. So I had my system that was running for RTU1 was running 24/7, but it's a 24/5 plant, not a 24/7. So the easy measure would be to put some kind of programming controller on there, a timer, or link it to a BAS. And I would get my saving purely by just reducing the 8,000 hours that I had in the previous slide to 6,000. And that gives me my new consumption. So I subtract that 196 I had before with the 135. So it gives me my 61,800 kilowatt hour savings. Now, one thing that's not shown on the slide, I need to insist, this will not be multiplied by your average electricity rate. Never, ever do that. You always consider your energy rate and your demand rate separately. This measure does not save demand because my system will be running in the daytime. So you will multiply that by the marginal rate for the energy, for the kWh. So if you're a Class A customer in Ontario, that'd be about 3.5 cents. If you're a Class B customer, so medium-sized building, small to medium-sized building, you would multiply that by about 12 cents. So big difference in the rate. So I forgot about that, Amanda. You have to be as careful as possible with all your energy numbers. But at the end of the day, if you come back here and you multiply by a blended electric rate, you actually just flush down the drain all of the work you did in evaluating your measures by using a rate that could be 4 times too high for the type of rate that you usually have. So if you have demand savings, you have to evaluate the demand savings individually, separately, and multiply that by the cost for your demand, which is the monthly cost. And if you're a Class A customer, you have to ask yourself, am I going to hit the 5 peaks? If so, how many peaks? And they're worth how much each? Anywhere between $60 and $100 per event. So those are the, say, a little warning that I forgot to mention. And once you've done that, you can build a table that will have all your measures, and all those measures will have savings based on the same approach we just saw for that one example for the RTU. But if it's a VFD, it will be using the affinity law. So that will give you a full picture of what can be done based on the information you've got and the accuracy that you wanted on your building by attacking the different saving mechanisms through different measures. And like I said, be careful about the cost saving. Make sure you use always the marginal rate, both for energy and for demand. That applies to natural gas, but to a lesser extent, most people have kind of a flat rate for natural gas. So that gives you the overall approach for estimating HVAC savings and using that 4-step, basically, energy auditing approach. So, Amanda, that's it for me.
Thank you so much. That was a very detailed, so much good information, a lot of good, just like firsthand account experiences, and also just taking a super complex topic and making it much more easily digestible, I feel like. And I hope also that the workbook is a good resource for you. If, I know that was quick, maybe not everything was caught. There will be a recording of this as well on the website, so feel free, to find it there. We are a little bit short for Q&A, but we did have some questions come through that I wanted to make sure we did talk about. So maybe I'll kind of start with the last ones and work back. There was a question around, and maybe you might have covered some of this since the question was asked, but feel free to reference back. What are resources to determine equipment average yearly efficiency instead of pulling nominal efficiency from equipment specs? And here we have specific to condensing boilers as an example. But yeah, are there resources to sort of be able to get that more accurate efficiency versus nominal efficiency from the specs?
So you have to start from the spec. And I'm going to go with the easy case. If it's a non-condensing boiler, reduce it if it's atmospheric. And I don't want to go too much in detail, but if you've got an atmospheric boiler, so you don't have a fan attached to the boiler, reduce it by 10%. If you've got a forced flow boiler, and obviously that can vary significantly, but 10% would be a safe reduction. 5% for the non-condensing forced draft boiler, so you've got a fan. Condensing boilers, you'll be either above 90%, and I would probably use like 92% if you're condensing, so your return is typically at 125 degrees all year long or below. If you're not at 125 or below, I could say 130, but let's say 125 and below, then you will have to judge how often am I below 125 or at 125 or below. And then you can prorate 85 and let's say 92 based on that percentage of time. If you're always below, if you're always above 125, let's say 130, use anywhere between 85 to 88%. 88% is the limit. Above 88%, you're condensing. And that means you need to be cold on your return. So it's a little more difficult with those condensing boilers. I know my answer is unfortunately a little more complex, but you need to know your return temperature, and then you will prorate between like that 85% and that 92% based on the amount of time you're in that condensing mode, which means cold return, and you're in that non-condensing mode, which means you're at 140 and above or 130 and above on your return.
Great. One other question we had are, what are typical factors which impede equipment from operating at peak efficiency? What are telling signs that equipment is operating at peak efficiency, or maybe telling signs that it's not operating at peak efficiency? Probably you could go both ways here.
Yeah. So I'd say the telling sign is if you bought some really expensive equipment, such as boilers and chillers, you've got a magnetic bearing chillers and you've got two of them and they always lead lag. You always only see one running. Well, they're definitely not running at peak efficiency. Same thing for boilers. You've got 3 boilers and you only see one running, and those are high efficiency equipment you paid for. You're not using them to their full extent. You got cooling towers and they have VFDs on the fan and you see only one running, and then it loads up and then only then does the second one starts. It's not running efficiency. The only exception to those is pumps. Like I said, pumps in parallel that shares common header and common discharge, you should not run them in parallel. The other type of equipment, you should almost always, if they're high efficiency equipment, running them in parallel. And the older equipment, you should lead lag most of the time.
Okay. One more I think we have time for. Can we spend some time going over the difference between nominal and ballasted efficiency / load? Why do equipment specs state nominal values instead of actual annual performance?
Because the only thing the manufacturers can do is report laboratory results. And the nominal efficiency is based on the lab results. In the field, that efficiency, depending on how you run the system, can so drastically go down, but they don't know how you're going to run it. So that's always the big unknown, is what is your annual efficiency. Even in recommissioning, it's very difficult to estimate the annual efficiency. So you really have to observe. If you go into a boiler room and you hear the boiler is cycling on and off, you're probably losing 15% of the efficiency of your boilers, regardless of the type, because of short cycling. So it's impossible for them to report annual efficiency, unfortunately. But in your calculation, you do have to make your own estimate of annual efficiency. And like I said, you should reduce at least 5%, like I said before, for the boilers. And for chillers, same thing applies. You get a chiller efficiency, but that's not the system efficiency. It's usually lower than the actual chiller efficiency. On a yearly basis, the chiller is not going to run like in a lab, in a test lab. It's usually going to run at different head pressure, condensing pressure, and evaporating pressure. So you'll usually be you could be at lower efficiency. I'm going to be careful about chillers. It's more difficult to evaluate, but you could definitely be lower than the nominal efficiency.
Okay, great. Thank you, Michelle, so much for that insight. We are pretty much at the end here, so I want to make sure we just quickly mention here, and I think Fatema is going to put it in the chat as well. There is free expert support available through Save on Energy. And as part of this, there's a really wonderful energy manager learning platform discussion forum, where if you have questions that kind of come up after the session or things that you didn't, get to ask, this is a great place to ask these types of questions and get a lot of support from folks like Michelle and other folks, other energy coaches and experts around some of these projects, not just estimating savings, but finding opportunities and all other sorts of kind of projects and topics. So would love for you to all, take a look at those resources and consider using those as they are available for you. And thanks, Michelle, for joining today and for all of your expert information, and for all of you who joined as well. It was a wonderful conversation. Thank you for your thoughtful questions, and we hope that you got a lot out of this session today. So yeah, I think thanks so much all, and we will let you all go and enjoy the rest of your day, and we hope to see you next time. Thanks.
Thank you, Amanda.
Thank you. Thank you, Juan, for joining. Thanks, Cameron.
And Cameron, in your comment there, just be careful. Parallel is only for high efficiency equipment. Lead lag for older equipment.
Famous last words.
Yes.
Excellent. Thanks, Dawn. Thank you, Ashish. Thank you, Ibrahim. Amazing. Thanks, Debbie. Cameron says noted, Michelle. So he kind of got that. Thanks, Kevin. Thanks so much. Excellent. Thank you, Mac. for the applause. That's wonderful. Thanks. Excellent.